Yeah, so we're talking about the new session with Johnson. So that's the thing. Who cares about that, right? You can find Taylor's theory everywhere. I don't think seeing a PowerPoint on it is really illuminating. So I said here are a few calculations I highlighted from last lecture, and he's going to go over those calculations after this lecture. So hopefully that's very useful to you because then you can actually from the previous lecture, you can really work out the steps. So similarly, today's lecture, I gave him 2 or 3 calculations, which I'll do, not fully, obviously, and then he'll work it out step by step and show you. And hopefully you'll get a better understanding of what I mean when I say the calculations are really long, right? Because then you'll actually see it worked out step by step. Okay, very good. Let's see, what else?
I don't think your video is pinned.
Oh, okay. Spotlight. There we go. Is it good now?
Yeah.
Okay, yeah, so that's that. Second thing, so is that okay? Is that better, do we think, or?
Yeah.
Okay, okay, good. Because I want you guys to see how to calculate the stuff that we're actually working out here. So, okay, very good, very good. So today he's gonna go over 2 things. He's gonna go over, remember at last lecture, we calculated the transition amplitude for a free particle, right? That was the first thing. And then I said, oh, if you use a relativistic energy, you get this result. And I didn't do it. He's going to do that step by step, literally step by step. Then I told you that the commutator between phi and pi was I times a delta function, right? So he's going to do that too, that calculation. Okay, so that will be very useful, hopefully. Okay, second, the homework for this week. So I'm not. So I was a little bit ambitious. I thought we were going to do all of spin 1/2 today. We're not. So here's the plan. I'm gonna derive the propagator. Hopefully that means something to you this week after reading. I'm gonna derive the Feynman propagator. That's what we're first gonna do. Then we're gonna talk about Dirac fields and spin 1/2. Uh, and then next week we're gonna quantize the Dirac field, right? And solve the Dirac equation. So today we're going to end up with, I'm going to end with showing you what the Dirac equation looks like. That's where we're going to end today, hopefully. Next week, we'll do some work with spin 1/2. And then week 5, we will do the S matrix and we'll derive the Feynman rules. That's like the big deal of the class, doing the S matrix, perturbation theory, deriving the Feynman rules. That won't be until week 5. So everything, I want to give us some room to breathe. So that means for the reading, basically, I want you to read anything you don't feel comfortable with, reread that. And then I'm going to assign some optional. Well, there's only the only mandatory reading I have written down here. Here, I wrote the reading down actually, because I always forget what chapters. The only reading I had here that's mandatory is from the book Srednicki, the book by Srednicki, chapters 2, 3, and these are optional. 33, 34, 35, 36. These are optional from Srednicki. Z 2.1, and then Weinberg 1.8, 1.10, 2.3, 2.4. So take a look at any of that if you want. These are more of the standard books. And then definitely read 2 and 3 in Srednicki. I would do that. They're very short. They're like 5 pages. And anything in Lancaster and Blundell that you don't feel like you really completely get. That's what you should do this week. I'm not going to give too much new reading because spin 1/2 is going to be split into 2 weeks. Okay, folks, any questions from last week? Okay, let's get started. I can erase this, right? Okay. It's hard because Jenna's the only one on camera, so she's the only one where I can get a gauge. So, okay, very good. Okay, so let's begin. So what did we do last week? Last week we did this operation called canonical quantization, right? That's the name for it. We did canonical quantization. We quantized a scalar field. That's what we did. And I mean, it wasn't a huge jump from quantum mechanics. It wasn't like that crazy. So today we're going to start deriving, right? Remember, our goal is to compute this guy. It's to compute these kinds of matrix elements, right? That's the goal right now. These correlation functions. That's where, oh, Bob's on camera too now. Okay, good. It's to compute these correlation functions. That's the goal, right? And you know, these are the direct analog to stuff like this. Right? So it's like we're just kind of taking it next level. Now to get from here to here is a big jump, right? We've gotten rid of wave functions, we've moved to fields, this is like, but hopefully you get how we move from here to here, okay? Okay, I trust that you get where we're going. So let's begin by finally kind of putting the pieces together for this, okay? Now, you did a lot of reading on the propagator. So you know the basic idea. What is a propagator? A propagator is something that is going to tell me that the amplitude from one point to another, from one in state to an out state. That's really it. Now, in a free theory, my in state is the same as the out state, right? I have no difference between the in state and the out state in the free theory, which is what we're doing. We're working in a free theory right now. We have no interaction. We have nothing. We just have some free scalar field theory. So we're going to start with this kind of quantity. We start in the vacuum, and we're going to compute the transition amplitude of this guy. Okay. The vacuum is the in state, the vacuum is the out state, and in the middle we have the commutator between two phi fields. And that will give us the amplitude of this process. Now, obviously, the amplitude of this process alone should be 0, right? Because this should not affect my in state, right? Because I'm getting the same out state back, right? And what do we know about the commutator? The commutator is 0, this commutator between two phi fields, phi of x and phi of y. Two phi fields are like kind of separated by what? By a space-like separation, right? So they can't affect each other causally. So if I can compute this, I can get the Feynman propagator, or almost the Feynman propagator. That's what I'm saying. Do we kind of get my motivation here? This is how I derived it.
Yeah.
Okay, good. So let us do that. Let's do this computation. This is one of the computations Johnson will do a deep dive into. Okay, so I'm going to compute it here. I'm going to pretty much do all the steps, but he will really hash it out. So this is one of them. So let's begin. We have some integral d3p over 2 pi cubed, 1 over 2 EP. Okay, I'm using his notation now, just to make you happy. E to the minus I, p dot x minus y. Minus e to the I, p dot x minus y. Hold on, let look at this for a second. I think I need one more integration thing. How do I want to do this? Do I want to do this? Yes. You know what we should do first? Sorry. This is what happens when you're trying to work things out on the fly. What we should do first is compute this. Let's just compute this guy, okay? No transition amplitude. I think that will be easier for me. Yes, definitely. Okay, so now we have d3p over 2 pi cubed. Very sorry. I usually don't use these errors, but 2 pi cubed. So this is for the two fields. Then I need 1 over square root 2ep, 1 over square root 2e cubed. You see why I'm doing this from this step, because now I'm explicitly integrating over both fields, right? One set of momentas for the second field, one set of momentas for the first field. Okay, so sorry about that. And of course, we're going to get some commutation relation of creation and annihilation operators, right? That's the whole idea. So I have some AP e to the minus ip dot x plus AP dagger e to the I p dot x. Okay, and then obviously this is going to commute with the mode expansion for the second field. And this is AQ e to the minus I p dot x plus AQ dagger e to the I p dot x. Okay, and this is a commutator, so I have my bracket. Now, well, these should really be y's, right? Because this has to do with the second field. Okay, suffice to say, let me work this out right now. Okay, you can work this out and you'll get this guy. You'll get d3p over 2 pi cubed, 1 over 2ep. E to the minus I p dot minus y minus e to the I p dot x minus y. This is something Johnson will work out. I'm just doing it on the fly. Yes, and no surprise, we can rewrite this relationship in the following way. Okay, so this should start to look familiar. This is starting to look like a Feynman propagator, right? This form. And I can write this guy as the difference between the Feynman propagators, D, right? You call D the Feynman propagator or the propagator in general. And this guy will obviously vanish and give 0, which is what we expect from this commutator when you compute it. Does that make sense? So I mean, I've shortened this calculation a lot. He's going to go through this. I'm just going off memory, which is what I do now. Now I just go off memory and fill in the answer. That's what I do. So what was I going to say? So this is what we expect. We expect this commutator to vanish. Nothing crazy here. I just renamed this quantity this, and I've renamed this quantity this. Okay. So now I have an expression for the commutator, which is this integral. Okay. The reason I wanted to start here was because now when I compute that matrix element, it's going to be easier because now I have an expression. So let's do that. So now we move to computing this, which is what I started the class with. Right? I already have an expression for this. And you know, this expression is just coming from the mode expansions, combining the exponentials and then taking the integrals. You should really get comfortable with these manipulations. And that's why with the Johnson sessions, hopefully you get comfortable with doing this kind of calculation. These are the kinds of important calculations you should learn right now. Okay, can I erase all of this up here? Are we good? Okay, so now let's compute that. You know what, let me write that up top. So let's compute that now. and we had a d3p over 2 pi cubed, 1 over 2 ep, e to the minus I p dot x minus y. That's the first term, just coming from our last calculation, minus e to the I p dot x minus y, right? That's just what we just calculated. And now I want to compute this. So I'm going to, so basically, let's just take a look really quick. This should be a 4-dimensional integral, right? Yes? Because this is relativistic. But you're like, hey, you have a D3P here. That's super weird. Where's P0? Where's the 0th component? Remember that the 0th component of the the momentum 4 vector is energy. So I've distributed, this is basically my P0 integration variable. So I'm going to distribute this over these terms. Okay, I'm going to split up the P0 part because the P0 part is really just an energy. Okay, so now I have integral d3p over 2 pi cubed, 1 over 2 ep. Let me just make sure I want to do this in the right fashion. Yes, e to the minus I, p dot x minus y, plus, I'm going to put a plus and you'll see why, 1 over minus 2 ep, e to the I p dot x minus y. This is evaluated at p0 equals e, p, and this is evaluated at p0 equals minus ep. Okay, that's my integral. I've just distributed the energy variable. And when you integrate this guy, you will get the following result. You get the integral d3p over 2 pi cubed, dp0 over 2 pi I, minus 1 over p squared plus m squared, e to the minus I p dot x minus y. No, not plus, minus m squared. Okay. How did I get from here to here? That's where Johnson will come in. Don't worry, it's a very simple thing. It's just a few steps. This should look very familiar now. Hopefully this start is looking familiar. I hope. This is very similar to the form of the propagator, the free propagator. So I hope this expression looks familiar, especially this term. Okay, so basically, I mean, what we're doing physically is very intuitive. Like even if you don't get the calculational bit, I'm starting with something very intuitive, right? Which is the transition amplitude from the vacuum state to the vacuum state. I want to put something in there that is not going to affect both states, the in state and the out state. But I also want to know something about what the kind of form of the amplitude will be. So that's really what the propagator is. So what do? I put in the commutator between two phi fields. I know that's not going to causally affect the in and the out state. And I get this guy. Okay, very good. So we're almost there. This is practically the form of the propagator. The only thing we have to do now is take care of our complex analysis to put this in the right form. Okay, so we derived that this guy now, this thing is just d4p. Now I'm going to put it all together. d4p over 2 pi to the 4th I'll write it this way for now. D3p over 2 pi cubed dp0 over 2 pi I minus 1 p squared plus m squared e to the minus I p dot x minus y. Now we define this guy now as the propagator d. Did they use d in your book?
No, I think they use G.
G?
Yeah.
Okay, doesn't matter. I call it.
Yeah.
So we call it d, okay? X minus y equals, we're going to have the heavy side step function, I'll explain why, x0 minus y0 times what we just derived. And that is the definition of the free propagator. Now, why did I include this step function? You're probably starting to go, oh no, we're going to get into the discussion about time with the propagator, right? Time becomes important. So I'm going to call that, this is actually going to be called d sub capital R. Okay, and why did I call it that? You might recall that there are two kinds of propagators, not kinds, but two distinctions. And I hate this word. You're probably like, why did they pick this word? There's the retarded propagator and the advanced propagator, right? The retarded propagator, which is what I labeled this, means that I've assumed that x0 is greater than y0. Means that I've assumed, therefore, that this difference is positive. Therefore, I've assumed that this propagator is taking me into the future. So a retarded propagator takes you into the future. An advanced propagator takes you into the past. So it's very counterintuitive. The advanced one takes you this way, the retarded one takes you this way. Okay? Did you read about that in the book? That's really important. Now we're going to have a mechanism that helps us and what is the step function saying? This step function is just basically there just to tell me that this guy better be positive. That's all. Right? Remember, because when a step function is positive, it equals 1. So I've only put this there just to like explicitly say that I need a positive time because it's a retarded propagator. That's it. Nothing crazy. Okay. We're going to have a mechanism to take care of this called time ordering, which I hope you've read about too. And time ordering basically means that I can get rid of this crap, this extra baggage. I'll give you a funny story. We had to do a homework problem on retarded and advanced propagators. Took me like 3-4 hours at the physics help room. So, I got a real deep dive on this because it's not exactly obvious what the distinction is, especially when you add time ordering. Then you really don't need the distinction because it's implicit in your notation. Okay, and we're going to talk about that in a second. Okay, now you should start to think about something really interesting. So remember, in quantum mechanics, when we solved scattering, right? How did we solve scattering equations? We wrote down some Hamiltonian. And what solved the scattering equation? Well, we had a Green's function. And what did that yield? That yielded some delta function. I hope this equation looks familiar. Okay, it's the same thing here. So what can I say now? I can say that the propagator is a Green's function. Okay, what do I mean by that? I mean, this is the second calculation Johnson will show you, and you can verify this, you should verify this. Let's say I have the Klein-Gordon operator, right? That's the Klein-Gordon operator, okay? Now, if I put in my propagator, we'll say it's the retarded propagator, okay? I should get, and I will get, minus I, Dirac delta, x minus y, okay? This will hold. Okay, that means that this propagator is a Green's function. Okay, therefore you might see it sometimes written as this, triangle x minus y, or that also explains why in your book you saw it written as g. Did they echo this sentiment that the propagator is a Green's function?
Yeah.
Okay, good. That's super important, right? Because it's telling us sort of the class of equations it can solve. And you can do this calculation. It's a little drawn out, but you can do it. Okay, so it's not a huge jump from ordinary quantum mechanics. Okay, we're not sort of going like 3 steps up. It's similar to stuff we've seen before. That's the idea. Okay, now what we need to do to this guy, and then we'll move on to spin 1/2, is we need to Feynmanize it. What do I mean by that? We need to take care of the complex analysis here. So I'm going to Feynmanize it, or what they call the Feynman prescription, and I'm going to put this propagator into the right form, okay? So let's do that. Any questions about any of this? Hopefully this is something that means something to you. It's not just some random thing I wrote on the board. Is that okay? Okay, good. And hopefully you're starting to get the sense that, hey, it's a good thing we learned quantum mechanics before we did this. Okay. maybe not. I don't know. Okay, so there's a problem with the propagator I wrote, and your complex analysis intuition might be kicking in, and you might be like, that's not good. So again, what did we, I'm just going to put this up top. We had d squared plus m squared. If I enact the I just get this guy. Okay, now your instincts might be going up because I have a pole in that propagator, and the pole is when p squared equals m squared, right? So I'm on mass shell and I have a pole. That's a problem. So I will rewrite the propagator in this way. D sub f for Feynman, because it's called the Feynman propagator, the free propagator. What kind of integration variable? Yeah, I want a d4p over 2 pi to the 4th times I. I need to add the I here because recall in my dp0, I had an I in the denominator, right? So to get rid of that I need to put an I up top. P squared minus m squared, same thing, except now we're going to add the Feynman prescription to make sure this pole doesn't happen. And we add a little I epsilon and push up the contour. Some small thing, okay? E to the minus I, p dot x minus y. Did they go over the Feynman prescription for the propagator? Okay, excellent, wonderful. So this is it. This is the free propagator. Woohoo! That's your first big derivation in field theory. And now you're like, oh, I'm starting to think a little bit because in the Feynman rules that Kyle pulled out of a hat, this guy was showing up in a lot of places. Gee, now you're starting to get a sense of the mechanics now, the real way this is going to start working. So this is the first calculation. I will make one distinction where I have to make the distinction between advanced and retarded propagators. Okay, so d of, we'll call this d of x minus y when x0 is greater than y0, and we'll call this d of y minus x when x0 is less than y0. And remember, we have the distinction between retarded and advanced propagators. Okay, now we can write the full propagator in this way. Theta x0 minus y0, our usual guy, 5x, 5y0 plus, so this is just the full propagator, y0 minus x0, our usual guy, again, y0. And now, instead of writing all of this crap, I can rewrite this guy in this way. 0, capital T, 5x, 5y, 0. Okay, so now I've introduced this new symbol t in this bottom corner. So this is really now what I'm writing down, called the time ordering symbol. Okay, and what does time ordering mean? First of all, it helps us get rid of all of this mess over here, right? That's like, it's just annoying baggage to carry. And so what this is telling me is later times go on the left, earlier times go on the right. So in this situation, the phi y field acts on the vacuum, then the phi x field acts on this guy. So it's just like quantum mechanics, right? When you had a string of operators. Okay. Okay, so we've done it. We have derived the propagator, and we have kind of done a first analysis of a quantum field theory. So do we have any questions before we move on to the treacheries of spin 1/2? We still don't know how to compute this for interactions. That's a big deal. And interactions are really what's interesting, right? Free theories are really boring because the universe is not a free theory. But we've computed this for a free theory now. Like we've done our goal, but for a free theory. So it's just a propagator. That's it. Hopefully this makes a little bit of sense after the reading. And you're starting to see, hopefully, also that if you didn't read, this is probably really esoteric, to say the least. Okay, can we move on? Shall we move on? Okay. Okay, so now we're going to go into the discussion of spin 1/2. And this is just to sort of get all the fields down, fermion fields and boson fields. And then we're going to talk about interactions, not next week, but the week after that. And we're going to talk about the S matrix. I think the book Lancaster calls it a hero for our times, the S matrix, which they're right, because it is. It was the way interactions were developed. So let's talk about, before we talk about spin 1/2, we need to talk about the Lorentz group. We need to do a deep dive into symmetry. So you guys know that symmetry is super important. I've said that, but you probably don't really yet have a deep understanding as to why. This is the first example where you'll start to see that, really start to see that, and you'll start to recognizing why symmetry can be so powerful. So hopefully you have some familiarity with the notion of a Lie algebra, right? If you do, then this will be very, very illuminating to you. If you don't, then you should go back and read it with this free week, so to speak, that I'm giving you to catch up. So let's just talk about Lorentz invariance for a little bit. The good thing is we did a lot of work with Lorentz invariance before last term. So a lot of this should be review. But basically, let's just start with the very basics. We say we have Lorentz invariance when this guy holds, right? Or basically, I mean, that's not really the statement that, you know what, I should write this. Lorentz invariance implies that when I boost a 4 vector, I'm really enacting a Lorentz transformation on it, right? That's really like what I mean. Okay. For the fields, I can write that in the following way. Phi of x goes to some phi prime of x equals phi times lambda minus 1 of x. So what do I mean by that? I'm just saying now that for the new field, all of the points now are transformed by lambda. That's all I'm saying. Okay, that's my notation. And so this is a very similar thing, except now we're transforming the field configuration. So any equation that's invariant under Lorentz transformations, right, that I can get back to utilizing Lorentz transformations is Lorentz invariant. Hopefully that's, I mean, we've gone through that. So So let's just redo some of those calculations. Let's do it for Klein-Gordon. Okay, let's do it for Klein-Gordon. So the Klein-Gordon Lagrangian, 1/2 m squared phi squared. Well, that's really easy. That's really easy how this will transform, right? Because what is this really saying? This is just 1/2 m squared phi of x squared. And so this will go to 1/2 m squared phi lambda minus 1 of x squared, right? I'm just saying that each one of the points are going to shift, right? Is that straightforward or? Okay. Now the second term is a little complicated because we have a derivative, right? So the second term in the Lagrangian, Klein-Gordon, is just d mu phi of x. Forget the square for now. And I'm going to have to bring in my Lorentz transformations, right? To show that this is Lorentz invariant. So I mean, it's not very complicated at all. I just get some lambda minus 1, mu, d nu, phi of lambda minus 1 x. Okay, this is how I would transform it, right? Under a Lorentz transformation. Notice I've written this guy now because we did it the other way. So lambda mu nu, this is how I would write the inverse. Okay, the rows and the columns switch. I'm just doing it a little backwards this time just to show you the other way because we did these calculations sort of the straightforward way, right? Okay, we also have our favorite identity, rho mu lambda minus 1 sigma nu g mu nu equals g rho sigma, right? We've written stuff like that as well. I just did it without the inverses, but I'm just showing you that just so you see it backwards too. It's good to see it both ways. And remember, we worked this out. I actually computed this with you, and we multiplied the Cauchys and the Cinches, and we just got back to the Minkowski metric. Okay, so now let's do d mu 5x squared, which is the actual term in the Lagrangian. Let's transform that. And now, as we know, it's going to carry the metric. We can always carry the metric with us. So I can write this out as g mu nu d mu phi prime, d nu phi prime, right? So I can transform this using the metric. And now to get back this guy in the new boosted frame, which will be the same thing, because this is just a Lorentz scalar, I have to invoke the Lorentz transformation. So let's do that. Let's invoke the Lorentz transformation. G mu nu, lambda minus 1. Ooh, what do I want to do? Rho. These are dummy indices, so sometimes you need to work it out in your head. Rho mu d rho phi. Lambda minus 1 sigma nu d sigma, sorry, phi, all times lambda minus 1 x, because this guy goes to the phi. Okay, I just pulled it out. And if you contract all the indices, just utilizing the equations we have, you get g rho sigma d rho d sigma phi times lambda minus 1 x. Okay, which is the same thing as this guy. It's the same thing. Okay, just move to some point. And that's all I've done. I've just shifted it. Right. So this proves that our Klein-Gordon terms are Lorentz invariant. We've done these calculations. I'm just doing it a little differently. Okay, very good. So if the action is Lorentz invariant, then obviously my Lagrangian is Lorentz invariant. So I can write down that my Lagrangian goes to Lagrangian. Oh, sorry, we can write this out as L of x with some x dependence goes to L of lambda minus 1 x. Did they show some of this in like the symmetry section of the book? Did they do some of these calculations? Or not?
I don't think so,
Okay.
but I might not be remembering. Right.
Okay, and we can also show that now the equation of motion is Lorentz invariant. So let's do that. Let's do that too. I mean, we've done this calculation before, but I'm going to do this in this crazy inverse way, just so you see it. Okay. Let's see how I want to do this. I know I'm going to need my best friend. What do I want there? Do I want a mu? Do I want a nu? So many choices, right? Let's do mu, and then we'll have sigma mu upstairs, d sigma phi oh, I need plus m squared phi and minus 1 x. Now I got to do my contractions. I get g nu sigma d nu d sigma plus m squared phi m to minus 1 x, which again is just the same thing. I've just shifted everything. Do these calculations make sense physically? Is it clear, or is it still a little fuzzy? What do I actually mean by Lorentz invariance? Okay, good. Because it's it's like we demand this from our equations. It's a symmetry we must demand to be consistent with SR. Okay, good. We've done this before, so I'm not gonna belabor the point now. Okay, now let's go to the next step. Okay. So phi of x is just some single component field, right? Now, if I had a multi-component field, it would transform much more complicated. I mean, not much more, but like I could do it in principle. For example, what if I wanted to transform J mu of x or A mu of x, where J mu of x is like a current, right? Or a current density, and A mu of x is a vector field. So now, like, what's the difference between this and this? Like, what do I mean by multi-component? This is one component. At the point x, there's one component, one value for phi, right? For A mu of x, it's a vector field. At the point x, there's 4 numbers at each point of x. That's all I'm saying. So like, okay, we've done different transformations. So like, what about 3D rotations? 3D rotations, I could write it down as some AI equals Rij Bj, where this is a rotation. And if I just want to put this in 3 plus 1, this would become A mu equals lambda mu nu B mu. B nu, sorry. Right, so I can transform this in any dimensional space. And so you should start to notice a trend here that is reflected in this statement. The more tensor indices I have, the more indices that I have that I need to transform, the more lambda matrices I have. Hopefully that's obvious because I need to contract more indices. So now let's start thinking about the set of Lorentz transformations. Let's start thinking about all of these Lorentz transformations. So how many Lorentz transformations do I have? Can someone tell me? in total? Well, there's 3 boosts, right? In 3 directions, X, Y, and Z. And then there's 3 rotations. So I have 6, right? Now, but now here's the thing. I basically have an infinite number of transformations in n dimensions, because like if I take 2 of those rotations and combine them, that's a new transformation. If I take them in this, I can basically just keep making different combinations of transformations. So the set of the lambda matrices put together in that way will form a group. We know the Lorentz group is SO3 plus 1. We know it's part of a group. We just haven't explored it more formally. So let's do that now. Let's kind of define these kinds of things. And you'll see that this is a huge motivation for spin 1/2. Okay, so let's consider that. Let's try and consider that kind of thing, okay? You know, and also there are many, many equations of motion that are Lorentz invariant. Many, many equations, right? For example, the Maxwell equations are Lorentz invariant. D mu F mu nu equals 0. Therefore, the Maxwell-Lagrangian is Lorentz invariant. L Maxwell equals minus 1/4 F mu nu squared, where F mu nu is the field strength tensor that goes d mu a nu minus d mu a mu. Right, so I can rewrite this Lagrangian, L Maxwell, as minus 1/4 d mu a mu minus d mu a mu squared, right? So even this guy is Lorentz invariant. This is just electricity and magnetism, right? So there are many, many Lorentz invariant equations we can write down. It's not just like there's like 5, you know, there's like infinitely many. You could sit down right now and test if this is Lorentz invariant just by writing down the matrix, contracting the indices. And you can write down maybe 20 Lagrangians that are Lorentz invariant right now. It's not that hard. How are we doing on time? Now we're getting into the nitty-gritty of today. Oh, good. Okay. So let's think generally. Let's think about some multi-component field. We'll call it capital Phi A of X, where A is telling me, you know, is this the first phi field, the second phi field, the third phi field, the fifth phi field? I just have an n number of phi fields, okay? And I'm going to transform this in the following way. I'm going to have some matrix MAB, labels the rows and columns of lambda on some new phi field, phi B. Sorry, I should probably write this way to be consistent. Okay, so what is this MAB? This is just some set of lambda matrices acting on phi B. So I'm just being a little bit more general here. I'm not being like that much more general. I'm being a little bit more general. So another way to write this would just be to say that phi goes to some m of lambda phi, where this is just some matrix acting on my second field, right? Okay, so let's just write down one kind of transformation. So let's say we have phi going, let's say we have phi going to m of lambda prime phi, which I will just rewrite as m of lambda double prime phi, where I define m of lambda double prime as m of lambda times m of lambda prime. The reason I'm writing it out in this way is to show you that now I've basically created a new transformation, which is the product of two starting transformations. So I'm showing you that I can just keep making up new transformations. And so in a sense, I'm forming a group using the group properties. This property is called closure, that all of the elements in the group can be combined to form new elements of the group. It's kind of like in set theory. If you have a bunch, actually, no, it's not. It's not the same. Okay, so what do we say now in group theory language? We say that these M matrices, so the M matrices form an n-dimensional representation of the Lorentz group. Okay, so this is now an n-dimensional representation, right? Because I don't even know the dimensionality of MAB. I don't know. It's just some infinite dimensional matrix, infinite rows and columns, just filled with lambdas. And now I can just keep making. Now this is like pretty useless physically. If the universe was an n-dimensional representation, we'd have a lot of issues. Because it couldn't compute anything. What could we compute? We could not compute anything. Luckily, we already kind of know that it's not, because we've used some group theory language. So let's look at one example. So now the most natural question you bright students will say is, okay, great. You showed me the infinite dimensional group, n-dimensional group. What are some finite representations? That's the natural thing to ask. So let's think about that. And you know where I'm going with this. The finite dimensional representations, the most natural one that we've worked with is spin 1/2 in quantum mechanics, where the dimensionality n is related to spin by 2s plus 1. Okay. Now this is super awesome because what's the dimensionality when s equals 1/2? What's the dimensionality? It's not n-dimensional now, matrices. What's the dimensionality of my matrices now in spin 1/2? Just plug in 1/2 in this. What do you get?
2-dimensional.
2, right? And what do we know the Pauli spin matrices are? They're 2 by 2, right? And what do we know as the group representations? SU2. Okay, so that is a finite dimensional representation. Okay. The only issue with quantum mechanical representation is it doesn't satisfy the Lorentz algebra at all. So we're going to have to promote it. But that's the idea. So we know from quantum mechanics that the spin 1/2. So for spin 1/2, you get n equals 2. And you get that spin 1/2 is a representation of the SU2 group, which we've seen. Where I can rewrite the matrices like this: U equals e to the minus I theta I sigma I over 2, where theta I is some infinitesimal parameter and sigma I are our Pauli spin matrices. These are unitary matrices, 2 by 2. Okay, hopefully this means something to you, because we've seen this in quantum mechanics when we did infinitesimal rotations, and hopefully Z showed this kind of expression. I hope so. This is very important. Okay, good. So for any continuous group, we can define a vector space made up of elements that are infinitely close to the identity element. Hopefully this means something to you as well. And that vector space defines the Lie algebra, okay? So now we have to go a little slow now. Now we have this matrix representation for SU2, which is the representation for spin 1/2. But now we want to write down a Lie algebra for rotations. And remember, it looks something like this. Ji Jj equals I epsilon Ijk Jk. Now, what are our J's? Our J's are super important. The J's are the generators of this algebra. And really, in reality, what are the generators? We remember from quantum mechanics, the generators are just basis vectors. And we also might recall from quantum mechanics, what are the generators in this situation? These J's, they're angular momentum operators. So angular momentum is a generator for rotations. Okay, that's an important, very important thing. And so now we have the group theory language for SU2. I can always recover this from this. I can get back my matrices. It's not a very hard process. So now for rotations, we know that the generator is angular momentum. Do we remember that from quantum mechanics? We did it, but did Z show this in his book? Hopefully, yeah, okay, very good, very good. And he showed this, good. Good, perfect, because that chapter was called Rotations and Lie algebra. So it was identical to this, where the generators are again angular momentum. Okay, now let's recall, now that we're creating the group theory language, recall that in quantum mechanics, we can actually write down angular momentum J as the cross product of a vector X cross P. And this is just equal to X cross minus I nabla, because that's the momentum operator, right? That's the momentum operator with H bar equal to 1. So remember, if you remember that far back, when we started the angular momentum unit, I wrote down the operators for angular momentum as like partial derivatives, right? And those partial derivatives were acting on the vector and transforming it, right? So that's what I'm saying here. We can write down the angular momentum operator in a differential form. So what do I really mean by this? Well, in 3 dimensions, I mean that Jij equals xi nabla j minus xj nabla I. So let's just play around with this for a second. Do we know what the nabla is? So I goes from 1 to 3, right? That's the first step. And then nabla nabla 1 is just del x. Nabla 2 is just del y. Nabla 3 is just del z, right? And then we know what these xi's and xj's are, right? X, y, and z, just labeling the numbers. Okay, so let's play around with this. If I have I and j both equal to 1, I get j11 equals x del x minus x del x. And this should be 0, which is true. Now recall, I never had this kind of angular momentum operator. Okay, so I'm just rewriting this. So let's just write one more down. If I have j12, well then I get what? I get x del y minus y del x, okay? And this does look like one of our angular momentum operators, right? This is kind of how we wrote them down. Now, if I want to move this to 3 plus 1 dimensions, that's super easy. Let's just change the indices. Let's have the vectors go to 4 vectors, and let's have the nablas go to space-time derivatives. Okay. Oh, and we're going to need a factor of I. You always need some factor of I to make the calculation work. Okay, great. So now this is the generator of rotations, right? Jij. This is the generator of boosts and rotations now. So these are the Lorentz generators. I've just sort of added one dimension. So this is the generator of my 3 boosts and 3 rotations. Cool. Okay, excellent. If this is a little foreign, read Z's book to get more in-depth insight. Okay, awesome. So what I'm saying is this will generate the rotations and the boosts. Okay, like any algebra, they must satisfy a commutation relation. You can already tell this is going to be such a nasty calculation. It's not even funny. Because I'm saying you're taking this times this, then minus this times this. So you have all those cross terms. So when I write down this really long expression, please, please don't be scared because you can see why it would be so annoying. I'm just gonna write it down. You can verify this. You should verify this. G new row. Oh God, J mu sigma. Okay, I really need to work out the indices really slowly. G mu rho, J mu sigma. This is just a commutation relation, so don't be alarmed. You can work this out with contracting all the indices. G nu sigma, J mu rho. What am I missing now? G mu sigma, yeah, J mu rho. Okay. Sure. Yes. Okay, good. Okay, it looks kind of crazy, but it's just contracting indices. It's nothing crazy with the metric. Okay, so all I'm saying is the Lorentz generators now, J mu nu, must satisfy this commutation relation, which we know in any algebra you have commutation relations. We will see the commutation relation or anti-commutation relation for the gamma matrices, for example. And maybe they said in the book that that's a Clifford algebra. Okay, whatever, it's just a name, who cares? You know, there's a very funny story. I had this buddy of mine, and I thought he was super smart because we would be walking in a park and he would see some bird in the lake. And he would be, so let's say the bird was a swan. He would be able to say the name of the bird in like 15 different languages. He'd say it in Japanese, he'd say it in Korean, he'd say it in French, he'd say it in German. And I'm listening to him and I'm going, whoa, oh. But then I said, oh, so do you know anything about the bird? He totally blanked. He knew nothing about the bird. He just knew all the names for it. So never worry about names. Names are stupid. You can look them up. Worry about getting what's really going on. I still laugh about that because he literally did not know anything about the bird. Okay, so now what's the next step? Let's make up a representation, shall we? Let's make up a finite dimensional representation. I give you very fair warning. This will look like I pulled it out of my hat. So last night I guessed like 10 different representations, guys. This one worked. So yes, it was very random. So this works. My notation's weird, so I'll just kind of show it. So let's write down a representation. Now that I have the algebra. Okay, let's write it down as J mu nu using my Lorentz generator, alpha beta. You'll see why I'm writing it like this. I delta mu alpha delta mu beta minus delta mu beta delta mu alpha. Okay, you'll be like, wow, this is super random. You're going to be so happy when you see that this works in like 2 minutes. Okay, so what am I saying here notationally? First of all, I'm writing down a representation. What is a representation? It's a set of matrices, right? That's what we just said. This is a matrix, albeit a very random one seemingly. The alpha and the beta are the locations in the matrix. So 0, 0, 1, 0, blah, blah, blah. And the mu and the nu I've denoted to indicate what transformation I'm doing. So is it a boost? Is it a rotation? Is it a boost or rotation? Remember, boosts we would write in this way, some J0I, right? Why would we write a boost in this way? Because for a boost, it's a one-directional transformation in the spatial direction, right? For a boost, my time component stays the same, right? You never transform time in a boost, right? We always say boost in the x direction or boost in the y direction, right? A rotation, on the other hand, would be some rotation of both indices, Jij. So the mu and the nu, I've written to indicate what transformation, Lorentz transformation I'm talking about. Okay. Now let's say I have a 4-vector V alpha. And let's say I want to enact an infinitesimal transformation on this guy. Did they show infinitesimal Lorentz transformations at all in Lancaster? No? Okay, whatever. Srednicki has it in those chapters I told you to read at the beginning of class. Okay, so we have, I'll represent an infinitesimal transformation like this. You'll see why in a second. Some omega mu nu, j mu nu, alpha beta to the new 4-vector beta. Okay, where omega mu nu is an anti-symmetric tensor, that means that omega mu nu equals minus omega nu nu. Okay, now you're like, what even is this? This is going to make a lot of sense in a second. First of all, let's just really break this down. What is this? This is like me saying V alpha equals, oh my gosh, equals lambda alpha beta V beta. Right, this is basically just a Lorentz transformation, except what's taken the lambda? It's this long term, okay? Is that okay? This is another kind of Lorentz transformation. It's just in a very weird form. I'll show you how it works. Okay, so let's do it for boosts. Let's do it for boosts. I told you that alpha and beta are the location in the matrix. Okay, so that we will worry about when we calculate. And I told you mu and nu I have to specify before because I have to specify the transformation that I want to do, right? That's only natural. So let's do a boost. And so I will say that omega mu nu, this anti-symmetric tensor, tells me about the infinitesimal rotation. This is the infinitesimal parameter that I'm rotating or boosting by. So let's say that omega 1, 0 equals minus omega 0, 1 equals beta, which is V over C, right? Just some boost in the x direction, right? The one direction, right? Okay. So now we have V alpha goes to some new 4-vector V beta. And it's going to transform by some matrix, right? That's the whole thing. This is a matrix. It's a representation. Okay? Shall we compute the matrix? Okay. Just to show you that this insane thing works. Okay, good. Let's do it. It's not that hard. Let's compute so I'm talking about alpha and beta. Let's compute J11. Let's compute J11. So for J11, I have delta 1, 1 minus I. Omega 1, 1 is what? Oh yeah, all other components of omega are just 0, right? Because this is just a boost parameter in that direction, right? So all other components of omega are 0. Does that make sense? Why I would do it like that? Okay, so since omega 0, 1 is 0, this whole term is just 0. So this just cancels. And I'm just left with delta 1, 1, which is what? 1. Do we see how I got that? Speak now and forever hold your peace. I'll explain it. It's not a problem. Okay, good, good. Okay, that means that just by logic, that means delta 2, 2 should be 1, delta 3, 3 should be 1, delta 4, what am I saying? Delta 0, 0, delta 2, 2, and delta 3, 3 should all be 1. Okay? Should just be 1. Now let's do what's really, and then all of the other terms should be 0, right? Except 1, 0, and 0, 1, right? Everything else should be 0. So let me fill in the other ones. So this is 0, 1. This will be something, and this will be something, and then everything else will be 0. Because why would these terms be 0? Because now let's just say I had alpha, beta. Let's say I wanted J 1, 3, right? For example. Well, then I have a delta 1, 3 minus this guy is just 0, right? And then delta 1, 3 is 0 because it's a Kronecker delta. Okay. Okay, now let's do the big ones. You should intuitively kind of know what we should get. So let's do omega 1, 0. So I now have a delta 1, 0 minus I beta, because that's omega 1, 0. J mu nu alpha beta, let's compute that. So J 1, 1, 1, 1. Oh, sorry, 1, 0. 1, 0 is what? Delta mu alpha is delta 1, 1. Delta nu beta is delta 0, 0. Minus delta mu beta is delta 1, 0. Oh, sorry, what is mu and beta? Oh my gosh. Mu is 1, beta is 0. Yes, and delta nu alpha, nu is 0, alpha is 1. Okay. So J1010, this guy's 0, because these Kronecker deltas are 0. This is 1 times 1, it's equal to 1. So now I have delta 1, 0 minus I times beta times 1 from this times V beta. Oh, sorry guys, this is times I, right? I forgot the factor of I. You see why I put that there? Because now I need this factor of I. Why? Because if I just had a 1, then I would get that this guy is just equal to beta. Oh, sorry, that this guy is equal to I beta, right? Because it's just minus I beta, right? But what does it mean to transform by I? Boost by I doesn't really mean anything. So that's why I needed the I to cancel it out. So minus I times I is 1. This is just 0, and I have a beta. So the 1, 0 component of my matrix is just beta. And so is the 0, 1. You can do the calculation backwards. Does it make sense how I got beta in that matrix? Yes? Okay, good. That's why I needed this random I. Now you see why I include random i's and I over 2's, and it's to make sure this works, that's all. Okay, this should be very exciting to you. Because now what we're really saying is this guy is just a matrix of Lorentz transformations. And when I wanted the boost in the x direction, I got that. I got just betas moving in the x direction. That's it. At the end of the day. Nothing crazy. So it works. So, when you see something like this, you get intimidated. You go, whoa, my God, what does that even mean? But really, it's just communicating something very, very simple and elegant. And again, what you should be saying is, I also have two more boosts in here. A boost in the X, a boost in the Z. Sorry, boost in the Y, boost in the Z. And then I also have 3 rotations here, rotation in X, Y, X, Z. So I'll just write down what you get for the rotation matrix. You should verify this. So for a rotation in X, Y, you get the following. You get that V alpha goes to, so this would be what? For a rotation in X, Y, that would mean that omega 2, 1 equals minus omega 1, 2 equals some infinitesimal parameter theta. And you would get 1, 0, 0, 0, 0, 1, minus theta, 0, 0, theta, 1, 0, 0, 0, 0, 1. Okay, that would be a rotation in XY. Okay. Also, this is a representation, a finite dimensional representation of the Lorentz group. Whew, man, I'm winded. How do we feel about all that? I know it's a lot, but that's what happens in this class. So I'm going to stop there. I'm going to start spin 1/2 next week, and we're going to do all of spin 1/2 next week, because frankly, it's not that much because we're not doing interactions. And then the week after that, we will do the S matrix. So what are we going to cover next week? First of all, do we have any questions about all of this? So what did we do today? We derived the Feynman propagator. That was your first big calculation in quantum field theory. So pat yourselves on the back. Honestly, to be honest with you, I find the calculation in quantum field theory to be much more intuitive than quantum mechanics for some reason. You know why? It's because quantum field theory is so much more symmetric than quantum mechanics. It really is. The fact that we have Lorentz invariance makes the calculations much easier, even though it doesn't look like it, but it really is. Okay, what else? Then we started talking about the Lorentz group. We did a deep dive, and Weinberg's book, the chapters I recommended in Weinberg are amazing. That's literally, if you read that chapter in Weinberg, you'll become an expert on the Lorentz group. You'll never have to read anything else about it because he really covered it. I put it in the reading. And so next week, we will do spin 1/2. We will canonically quantize a spin 1/2 field, a fermion field. And Dirac asked a very simple question. This is what Dirac asked. He sat down and Dirac said, can I write down a finite dimensional representation of spin 1/2? That's all he asked. And he started creating an algebra. You will see, and you should know, that fermions satisfy anti-commutation relations. And you will also see, as you know, that the generators in the Dirac algebra are these things called S mu nu. Did you see S mu nu? Okay, they're spinor generators, basically. And we'll also see that spinors transform very strangely. Now, the representation we will work in for spin 1/2 is called the chiral representation. I think they mentioned that. Now, chiral is Greek for handedness, left-handed or right-handed. And hopefully you're going, oh, okay, because we have left-handed and right-handed spinors that we must transform, right? Where psi is some 4-component spinor field. Okay, so we will do all of that good stuff next week. I will be here tomorrow morning for your questions. I think last week was really great. We had some nice questions. We had some good discussion. And yeah, that's it. I was going to start spin 1/2 today, but I said, you know what? Let's do it next week because we don't have a lot of time, and I'll be able to do all of spin 1/2 in 1 week. And then the week after that, we will do the big thing, S matrix, perturbation theory, deriving the Feynman rules. And the name Wick will be your worst nightmare. Just saying. Okay, that's all I have. So Johnson, if you want to start now, or I think you should give them a break until 11, a 5-minute break. This was very, very rapid, so.
Yeah, that sounds good.
Okay. Any questions before I zone out?
Yeah, is there a PDF online for the Anthony's, book, the nutshell for physics?
Yes. Every book I've told you has a PDF online. Every single one. If you can't find it, send me an email and I'll send you it if you can't find it. Literally every single one. So I like Srednicki, to be honest with you. Well, I really like Weinberg. Weinberg's my favorite, but don't read Weinberg until you've read something else. Then you won't get anything out of Weinberg. It will be like water going through marbles. I had a professor like that once. I said his lectures were like water going through marbles. I would hear him. I hope it's not like that in our class. Oh my gosh, please tell me. But I would hear him. He would write equations from the top left to the bottom right, okay? Straight equations, he would never write a word. And I kind of do that. I'm not like that. Straight equations. He would not say a word. If you raised your hand to ask a question, he'd ignore you. He'd get in right on time, he'd leave right on time, and he'd drive his sports car away in the middle of Manhattan. This guy's named Norman Christ. Oh no, I'm on recording. I take myself off recording because I work with him. So.